I'm Joanne. I did my undergraduate degree here in Maths and I've just started an integrated PhD in statistics. And today I'm going to talk about Bayesian statistics, which I first learned about this time last year in the module Statistical Inference. Probability that each random variable equals the observed value, and then because they're identically distributed, this is just the same as the product that each random variable, that x is xi because they all have the same distribution, and then we can say this is the product from I equals 1 to n of fx of xi because we said the distribution of x we can write as fx. So we can also make further assumptions. So we can propose a distribution for x, so give a form for fx. And here this will depend on just one unknown parameter, which we will call theta. The values that theta can take we call the parameter space, so it could be the real line or integers or the positive real line or anything. So now instead of using the data to learn about fx, we want to use the data to learn about theta, because if we know theta then we know the distribution. And this is called parametric statistical inference. And lastly, we'll write the joint distribution as fx of x given theta to show that we're now dependent on theta. Okay, so we got that out of the way. So if you're doing a maths degree, what you would have been learning in the first 2 years if you studied statistics is actually called classical or frequentist inference, where probability statements are based on long-run average frequencies. So for example, if I'm tossing a coin, I would expect the proportion of heads to tend to a half as I do more tosses. And we treat all the values of theta in the parameter space as being equally important, so we don't say that any value of theta is more likely than any other. And importantly, we treat theta as being unknown but fixed. So it's some value that we don't know, but we assume that it is constant. And all we have to learn about theta is the data. But Bayesian inference is different because we can incorporate prior information. So it makes use of subjective probability statements that are based on opinion, and we assume there is some information about theta that we have before we start. And we characterize this through the prior distribution, pi of theta. And but it's the same function, but we interpret it as a function of theta given x rather than x given theta. So we want to combine these in a formula. So Bayes Theorem tells us that the posterior distribution of theta given x is given by this. So the prior times the likelihood divided by the integral over theta in our parameter space of the prior times the likelihood. So I'm going to prove this now. Okay, but before I do that, we've got the integral, so we are assuming that theta is continuous. Theta is a continuous random variable, and if it wasn't, then we would just replace the integral with a sum. So now I'll prove it. So this is what we want to prove, and we will need to use the multiplication rule, which you might have seen. So the probability of two events A and B is the probability of B times the probability of A given B, and we can also, it's equivalently the probability of A times the probability of B given A, and we'll use that to prove this. So we're going to let A be theta and B be x. So we have the probability of theta and x is the probability of x times the probability of theta given x. And then that's the same as the probability of theta times the probability of x given theta. And then we're going to divide both of these by the probability of x. So we get the probability of theta given x is the probability of theta times the probability of x given theta divided by the probability of x. Now we can rewrite this probability of x in terms of theta. So if we keep the numerator the same, then we can write this as an integral. So if we integrate over theta of the probability of x and theta, then this is the same thing, because we're just integrating theta out of the joint distribution, which will just give us the probability of x again. And then this x and theta is the same as this, it's just swapped them the other way around. So we can replace this with one of these two expressions, and I will choose this one. So we've got the same numerator, and then we're writing this as probability of theta, probability of x given theta d theta. And now we're basically there, we just need to replace these with the notation that we already defined. So the probability of theta given x is just the posterior distribution. So this is pi of theta given x. And then p of theta is pi of theta. And then p of x given theta is our joint distribution function, which we said we were going to call the likelihood because we changed the conditioning. So this is the likelihood of theta given x, and then we've got the same thing on the bottom. Okay, and then we've proved it, and that's the result we had there. Okay, so it does look quite complicated, and if you were going to use that in practice, especially with the integral on the bottom, it might be a bit difficult. But we can simplify it because the denominator doesn't depend on theta at all. So before it was just the probability of x, and then we just introduced theta into it, but we're integrating theta out. So the denominator is just a constant. So we can say that pi of theta given x is just proportional to pi of theta times the likelihood. And all the denominator is a normalizing constant, so it just ensures that the density integrates to 1. Because if we integrated pi of theta given x over theta, then the numerator and denominator would just cancel and you'd get 1. So that's the only reason why that's there, and we can just ignore it until the end and just work with theta. Because once we get our function of theta, we call that the core of the distribution, and then we can use that to identify what the distribution is if it is a known distribution. So the key thing to take away is that the posterior is proportional to the prior times the likelihood. So here's an illustration. So our prior is the blue curve, the likelihood is the red curve, and then the posterior is the black curve. So the prior is quite vague, it's not telling us that much about the true value of theta. And then the data has got a very well-defined peak around 5, as this is looking at how likely the data makes each value of theta. And then the posterior, which is our updated prior, you can see that's kind of shifted to take the shape of the likelihood. And the reason it would do this in practice is if your prior isn't telling you much, but also if you have a lot of data, then the posterior will move towards the data, and the prior won't matter so much, it won't influence the result as much. Okay, so we can do an example now. So suppose x1 to xn are IID random variables from the Bernoulli distribution with parameter theta, and our prior distribution for theta will be the beta alpha beta distribution, which has this PDF. So if you haven't seen the function on the left before, it's called the gamma function, and I'll just define it. We don't need it, but just so you know what it is. Is the integral from 0 to infinity of x to the alpha minus 1 e to the minus x dx. So that's all that means. Okay, so we've got the prior. We need to find the likelihood first, and then we can multiply them together. So the Bernoulli distribution, if a random variable follows the Bernoulli distribution, that means that it can take the value either 0 or 1, depending on if we have a success or a failure, and theta is the probability of success. So if we're trying to find the probability mass function for the Bernoulli distribution, we want something that will be theta when xi is 1, and 1 minus theta when xi is 0. And if you look at the function there, then you should be able to see that if we evaluate that as 0, then we get 1 minus theta, and if we evaluate it at 1, we get theta. So to find the likelihood, we need to multiply this, take the product from I equals 1 to n, so across all our data. And if you do that, then you've got a product of theta, so you've got theta to the power x1 times theta to the power x2 all the way up to xn, which is theta to the power of x1 plus x2 up to xn, so theta to the power of the sum of the xi's, and then you've got 1 minus theta to the power 1 minus x1 plus 1 minus x2 all the way up to 1 minus xn, which is n minus the sum of the xi's. So now we can find the posterior. So pi of theta given x is proportional to the prior times likelihood. So for pi of theta, we can just ignore the gamma functions because they are just the normalizing constant, so they're not going to affect this proportionality, so we can just take the theta terms. So theta to the alpha minus 1, 1 minus theta to the beta minus 1. And then the likelihood, we will put that all in. So theta to the sum of the xi's, 1 minus theta to the n minus the sum of the xi's. So then we want to combine the theta terms and the 1 minus theta terms. So we just add the exponents. So we've got theta to the power alpha plus the sum of the xi's minus 1, and 1 minus theta to the beta plus n minus the sum of the xi's minus 1. So we've got the core of our posterior distribution, and now we want to try and identify it. And I've chosen a nice example because this is one of the distributions that is on the board. So you've got a 50-50 chance of getting it right. So can anyone say which one they think it is? So based on the form, what family does it look like it's from? So we've got the beta or the Bernoulli. Yes, beta. So we've got, if you call this alpha star and this beta star, then we've got theta to the power of something minus 1 times 1 minus theta to the power of something else minus 1. So this is the beta distribution proportional to the beta distribution, and our first parameter is alpha plus the sum of the xi's, and then our second parameter is beta plus n minus the sum of the xi's. And in fact, the posterior distribution is actually the beta distribution, because all we're missing is the proportion, the normalizing constant that makes it integrate to 1. So we can just say that theta given x follows the beta distribution with these parameters. Okay, so what you might notice is that in this example, the prior was a beta distribution, and so was the posterior. And when we have that, we say that the prior distribution is a conjugate prior of theta. And all the algebra works out very nicely when we have conjugate priors. There's some other common examples, which are the normal, and Poisson gamma. So what I mean by that is that if our data follows a normal distribution, and we specify a normal prior, then the posterior will also be normal. And if our data follow a Poisson distribution, and we specify a gamma prior, then the posterior will also be gamma. So I've done a table to illustrate this. So if our random variables follow a normal distribution with mean theta and variance sigma squared, then this means that theta lies on the real line, so it can be any real number. And then if we specify a normal prior for theta, so say that theta follows the normal distribution with parameters alpha and beta, then that again tells us that theta must be on the real line, because the domain of the normal distribution is the real line. And then we will also get a normal posterior for theta, which will again have the same domain. If our data followed a Poisson distribution with parameter theta, that means that theta has to be a positive real number, because theta is a rate in this case. And then I could specify a gamma distribution for theta, and the domain for the gamma distribution is the positive real line. And then the posterior, because it's conjugate, will also be gamma with different parameters, and will have the same domain. And then the example that we did, where x1 to xn were Bernoulli, theta was a probability, so it's between 0 and 1. The prior we specified was the beta distribution, and that has a domain of the interval 0 and 1. And then the posterior we found was also a beta distribution with different parameters. So you can see it's important to make sure that the ranges align. So what is implied by the distribution of the random variables and what you imply by your prior distribution are the same. Okay, so once we've got this posterior distribution, what can we do with it? So it underpins what we do in Bayesian inference, and we could use the mean of the posterior distribution or the mode to estimate theta. But the mean has a very nice property, because you can write it as a weighted average of the prior mean and the sample mean. So we can do this for our example. So if we want the expectation of this distribution, you take the first parameter divided by the sum of the two parameters. So you have alpha plus the sum of the xi's divided by the sum of these two. So the sum of the xi's will cancel out, so you just get alpha plus beta plus n. And we want to write this as a linear combination of the prior mean and the sample mean. So our prior was beta with parameters alpha and beta, so the expectation of that is alpha over alpha plus beta. And then, so we want something times this, and then we want something else times the sample mean, which is the mean of our data, which is the sum of the xi's over n. So we want to have this denominator, and we can see that these two terms don't have the denominator that we want. So it would be a good idea to multiply by the denominator so that these will cancel, and then divide by what we want, which is alpha plus beta plus n. And then we can do the same thing here. So times up by the n and divide by alpha plus beta plus n, and then that gives us what we've got here, because then you've just got alpha plus the sum of the xi's divided by alpha plus beta plus n, with these cancelling. So if we call this w, then this will be 1 minus w, because if we add these two together, then we have alpha plus beta plus n divided by alpha plus beta plus n, which is 1. So can anyone tell me what would happen as n goes to infinity? What would happen to w? Yeah. Yeah, so as n goes to infinity, which means we get more data, w will go to 0, and 1 minus w will therefore go to 1, which means we're going to put more weight on the sample mean. So if you have more data, your prior distribution is less important, and your posterior mean will have more weight on the data, which is quite nice, because if we're worried about specifying our prior, then it doesn't matter too much if you have a lot of data. Okay, so Bayesian inference has a lot of nice properties, and I think things are a lot easier to understand compared to in frequentist inference. So with hypothesis testing, we're trying to decide whether the null hypothesis H0 or the alternative hypothesis H1, which one is more likely. So H0 specifies that theta is in some range theta 0, and H1 specifies that theta is in some other range theta 1. Now, from what you will have learned so far, if you study maths or statistics, then you would have to find a test statistic which has a known distribution, and then you would calculate an observed value of that and compare that to a critical value from that known distribution, and then depending on whether it was more or less than that, you would reject your null hypothesis or not, which is quite involved. But with a Bayesian approach, we have a distribution for theta. So if I want to know what's the probability that theta is in theta 0, all I have to do is integrate over my posterior distribution over the range theta 0. And similarly, the probability of H1, given my data, I just integrate my posterior over theta 1. So it's a lot more straightforward. And then we can also compare confidence intervals and credible intervals. So in a frequentist approach, you can define a 95% confidence interval for theta. So I'll call the interval L of x, U of x, where L and U are functions of our random variables. And then we define the 95% confidence interval to be that the probability that theta is between L of x and U of x is 0.95. But what is random here is L of x and U of x, because they're functions of random variables. So we need to evaluate this at observed values. So we need to observe some data, and then we can find out what this interval is. But that would just be one interval, and you can't say that, because we're viewing theta as a constant, we can't say the probability that theta lies between two numbers is 0.95, because theta is either in that interval or it's not. So the probability is either 0 or 1. So what you would have to do in practice is get repeated samples of your data and then calculate multiple intervals, and then we would say that 95% of those intervals would contain the true value of theta. So something a bit like this, where most of the intervals cross the red line, which is the true value of theta, but then you have the odd one which doesn't include it at all. In a Bayesian approach, we have a credible interval instead of confidence interval, and I'll call it the interval LU, and L and U are just constants, and we have the probability that theta lies between L and U is 0.95. But what's random here now is not, well, we're treating theta as a random variable, so theta is the thing that's random, and we don't need to come up with a different meaning, because that is exactly what it means, that we calculate this interval once, and then the probability that theta is in that interval is 0.95. And so here's some examples of what you could have. So you've got your posterior distribution, and then there's a 95% chance of theta lying in that red region. So the idea is that in a frequentist approach, your theta you're saying is fixed, So you have to calculate lots of different intervals, and then 95% of those you will cover theta, whereas in the Bayesian approach, your interval is fixed, but your theta is random, so your theta is moving around, and there's a 95% chance it will fall in your interval. And I think Bayesian is more straightforward. And then lastly, we can look at prediction. So suppose I've got another random variable xn plus 1, and I'm going to get an observation from it called lowercase xn plus 1. And I want to know what its predictive distribution is given my data. Now we know its density function will be the same. So I'm assuming that its xn plus 1 has the same distribution of x1 to xn, and it's also independent, so the density will just be fx of xn plus 1 given theta. And then I won't prove it, but you can show that the predictive distribution is the integral over the values of theta of the density function times the posterior distribution. So the idea is that we are averaging the density, and each value of theta, we're weighting it by how likely the posterior makes that value of theta. So it's like a weighted average. So now we can get on to the sunrise problem. So we're trying to answer the question, what is the probability that the sun will rise tomorrow? And I hope I've converted you all to be Bayesians, so now we can evaluate the plausibility of this statement, the sun will rise tomorrow. All we need is a hypothetical random process that determines whether the sun rises or not. And then we can have some data, so things we know about the sun rising in the past, combine that with a prior for theta to get a posterior, and then we can calculate a predicted probability that the sun will rise tomorrow. It was first introduced by Laplace in the 18th century, and he applied his rule of succession to it. So we need to understand that first. So if we go back to the example we did, the Bernoulli beta example, this was our prior distribution, and we're going to put some numbers on this. So I'm going to let alpha and beta be 1, and this means that my prior distribution is 1. So the theta to the power of alpha minus 1 will just become theta to the power of 0, which is 1, and then 1 minus theta will be 1 minus theta to the power of 0, which is 1. And then the gamma term, you have gamma of 2 over gamma of 1 times gamma of 1, and you have to take my word for it that those are all 1. So you just end up with 1. So it's a flat prior, so it looks like so theta is between 0 and 1, and we're saying that no value of theta is preferred over any other, that they're all equally likely. Okay, so then our data we're going to assume, because our data follows a Bernoulli distribution, so we're looking at successes and failures. So we're going to assume that in the past we observed n successes, so all of our xi's were 1. This was our posterior distribution that we had before, and you can show that the posterior distribution is just the expectation of this, sorry, the predictive distribution is just the expectation of the posterior distribution. So because our random variable xn plus 1 is discrete, we have a probability mass function. So we're either we want to know what's the probability that xn plus 1 is 1 or 0. So given our data, and the probability that it's 1 is just the expectation of the posterior, which we found before was alpha plus the sum of the xi's divided by alpha plus beta plus n. So if we substitute in our values for alpha and beta and xi, then we get n plus 1 over n plus 2, because the sum of the xi's is n, because we said that all the xi's were 1, and then alpha and beta are 1. So this relates to the sunrise problem, because we're saying that we have observed the sun rise n times in the past, and we're saying the probability that the sun rises is theta, and then we've had n successes, and then the probability that xn plus 1 is 1 is the probability that tomorrow we observe another success, so the sun rises again, given that we've observed the sunrise n times, and that is n plus 1 over n plus 2. So as n goes to infinity, this probability will tend to 1. So if we've seen the sun rise more times, then it will be more likely to rise again, which is what Laplace's rule of succession means. That the more often something happens, the more likely it is to happen again. So this is what we found for our probability, and as of today I have lived for 7,759 days, so you can work out my birthday if you have some time. So for me, the probability that the sun will rise tomorrow is 7,759 plus 1 divided by 7,759 plus 2, which is about 99.987%. However, Laplace realised that this was a misuse of his rule of succession because it doesn't use all the prior information that we have. So the point is that I get this probability based on my life, but if I, say, used the number of days my mum had seen the sunrise, I would get a different answer, and it would be closer to 1. And what Laplace said was that, but this number, the probability of the sun coming up tomorrow, is far greater for him who, seeing in the totality of phenomena the principle regulating the days and seasons, realises that nothing at the present moment can arrest the course of it. So basically, if you just look at the history of the Earth and you've seen the sun's risen for so many days, and you look at the science behind it all, then really nothing's going to stop it rising tomorrow. So this is known as a reference class problem, because we get different answers depending on whose experience we use. So we could use one person, we could use the whole of humanity, or we could use the experience of the Earth, and then each one would give us a different plausibility. And the Bayesian principle is that our probability is conditional on what one knows, but what we know varies between people, so we get different answers. So just some advantages and disadvantages of Bayesian inference based on what we've seen. So a key advantage is that you can incorporate prior information, and that you don't have to rely on asymptotic results because everything we do is exact. And because we get a distribution for theta, we have a variance, and we can quantify how certain we are about the value of theta. And I hope I convinced you that things like hypothesis testing, credible intervals are a lot more easy to understand than in the frequentist approach. But a key disadvantage is that it is difficult to choose a prior distribution, and the prior could have a big impact if you don't have much data, because then we'd be putting more weight on the prior mean, so it would be more important. And similarly, if we have a lot of data, then the prior doesn't really matter at all, and you'd get similar results to what you would get for frequentist inference. So you might ask, why would you need to use Bayesian anyway? And lastly, the computational cost. So I've been doing something lately, learning about something called Markov chain Monte Carlo, which is a computational method that you have to use when your posterior doesn't take a known form. So you found the posterior, but you can't just say it's a particular distribution because it's so complex, and so you have to sample from it so that you can learn about it. And like trying to code that on R it takes quite a long time to do, so there is a computational cost. So I have used Bayesian inference mainly in forecasting. So I've looked at forecasting pollutant levels like ozone levels based on previous observations like in past hours. And my PhD project is about forecasting fertility rates. So I form my prior distribution based on the historical data to try and forecast them into the future. And then I had a look on Wikipedia to see what other uses of Bayesian inference there are. And Wikipedia told me that you can use it in artificial intelligence and expert systems, pattern recognition, and Monte Carlo simulation methods, which is what I just talked about. And also, apparently you can use it in the courtroom, and that jurors use it of statistics. And if you go to level 9 of the maths building, which is where all the statistics lecturers are, I think they're all Bayesians up there, so they would tell you how good it is as well.